Good. Okay, so the problem is now all this was motivation. What we want to study now is this problem. To calculate the number of microstates compatible with a certain level of energy given by the number of spins up. In other words, this function g of n plus, what we said is the combinatorial n plus, which is n factorial over n plus factorial and minus factorial. And at the end, I will replace it. I will replace n plus by n over 2 plus s. But remember, I want to study that function, g of ns, when n is a number too huge to actually write explicitly. It's 10 to the 23, so factorials cannot be calculated. And s is a number which is quite smaller than n. Okay, that's my problem, to approximate that. So, and what I will do is something that people do many times, which is instead of just calculating this, I will calculate the logarithm of this quantity of g of ns or g of n plus, which are two ways of referring to the same. Why do I use the logarithm? First of all, there is no harm. It will allow me to do the mathematics easily. At the end, I exponentiate what I get and I go back. But as I told you, logarithms will be very useful because when, and this will be next class, when we start considering what happens when you have two systems that are in contact and they can exchange energy, you will see that then the problem is we will know how many states this system has and how many states this system has, and we will need to know how many states the total system has. And obviously, the total number, if this can be in 20 states and this can be in 30, the total system, if they are not interacting, can be in 20 times 30. So the total g will be multiplicative. That means that logarithm of g will be additive. So if you calculate log of g for one system and log of g for another, they are additive functions. The log of g of a complex system is the sum of the ln of g of the different parts. So they have advantages to use logarithms, but eventually we'll go to the g. So in order to do that, obviously what I will use is the Stirling approximation. That's why we developed it. Remember that n factorial was, I write it quickly for you, was n to the n square root of 2 pi n e to the minus n plus corrections, which I will not bother with. I will not use this term. So, but ln n factorial will then be n plus 1/2, that's what we did last time, ln n minus n, coming from here, plus ln of square root of 2 pi. Ln of square root of 2 pi, and the ln of 1/2 n gives me this 1/2 here. So this is the Stirling approximation, and I will have to replace it in the expression I have, which contains a bunch of factorials. Okay, so remember that I had 3 factorials there because my ln of g is ln of n factorial minus ln of n plus factorial minus ln of n minus factorial. That's the expression I have, and in each one of those 3 terms I will use the Stirling approximation. So that's what I'm going to do now. So I will have n plus 1 ln n here, and from here I will pick a minus n plus 1/2 ln n plus minus n minus plus 1/2 ln n minus, and here I have minus n plus n plus n minus that cancel. So the part that was minus n, I don't need to write it, but here I get logarithm of square root of 2 pi minus logarithm of square root of 2 pi minus another, so I get minus ln of square root of 2 pi. So this is the expression. Okay, so far all I've done is use the ln, but no expansion. All I used is the Stirling approximation to the logarithms. Okay, and now is where I start manipulating with things. I will try to point the details, but if you get lost, look it up in the book. Don't worry too much. This is just mathematical details, but I want to express things in terms of n plus over n and n minus over n and things like that. So, for example, one thing which I will do is write this number as m plus 1/2 plus n and minus plus 1/2 minus 1/2. Okay? This is n plus n minus is the n, 1/2 minus 1/2. Why do I want that? Because then the term n plus 1/2, I will combine it with this. And the term n minus plus 1/2, I will combine it with this. And so what I will get, when I combine those two, I will get, and still is an exact thing, I will get minus n plus 1/2 ln n plus over n, because I have ln n plus and here I have ln n, and this is with the minus sign and this is the plus. I'll have here the term minus n minus plus 1/2 ln n minus over n, and I took care of this and this. All I have left is this minus 1/2 ln n. So all I have left is this and minus 1/2 ln n, which is ln of square root of n, so I can put it here. So I have minus ln square root of 2 pi n. This n comes from this 1/2. 1/2 ln n is ln of square root of n. So, and this has a minus, so I combine it. Did I write it right? Yes. Or I could have written 1/2 the logarithm of 2 pi n. But so far, this is exact. All I did is I grouped in a different way the terms. But you see, I am going in the direction I want because the line that I'm missing. Oof. And that didn't let me go. Oh, the bar disappeared. Let me get it from here. That's what I like. But the other one worked perfectly. I didn't have all these problems. This. Good. So, in this expression, which is exact, now I am ready to replace things by s. I can introduce the variable s. So n plus, I will replace it by n over 2 plus s, and n minus by n over 2 minus s. So I'm getting ready to do an expansion. So let me actually do this auxiliary thing. The ln of n plus over n, because I need this for the ln of n minus over n. I will write both together. So together, I mean, instead of writing the expression for this and the expression for this, I'll put them plus minus, and then we will replace each one in the proper place. Okay? This is n plus or n minus over n is the logarithm of 1/2 plus or minus S over n. Because remember, n plus was n over 2 plus s. So when I divide by n, I get 1/2 plus or minus, according to this, s over n. Okay? And this I can even write one more step. So no approximation, okay? I just replace n plus by the definition. I will take the common factor 1/2. This is logarithm of 1/2 plus the logarithm of 1 plus or minus 2s over n. I took a common factor 1/2. Am I correct? Yes. And this I can write as minus ln 2. Even more. So far I am playing with numbers. Ln of n plus over n or n minus over n is any of these. So since I have these two things here, that's what I'm going to replace. So I will get, and actually at this point I can do my first expansion. Because remember, I said I want to study this when s is a number much smaller than n. So until now, everything was exact. Now I'm saying, let me consider that s is a number that is much smaller than n. So this is ln of 1 plus something very small. And I am doing an expansion. The ln of 1 plus x, as you remember, is x minus x squared over 2 plus correction. So this will be approximately minus ln 2 plus or minus 2s over n, again plus or minus the square of this over 2, which is 2s squared with a minus sign, because in both cases you have ln of 1 plus x is x minus x squared over 2. Ln of 1 minus x is minus x squared over 2. So this minus appears both in this case and in that case. Did I get it right? Yes. Okay, so now is when I go and I need to plug this expression in my original expression. So let me see if you can see where I was. I will do this, it doesn't like it. Can you move it down? But not too much. I want to show, yeah, that I am plugging in the upper expression. Okay, so and when I replace that, I will obtain, show it a little, move it a little bit up so people can see what I do. So the first term is when I put minus ln 2. So when I put minus ln 2, I have a minus, so this is a plus. I have n plus n minus plus 1/2 is n plus 1. So the first term will be n plus 1 ln 2. That's coming from this term. So just from this term here, I will get an n plus 1 ln 2. Just from plugging this part here. Okay? Now I have to plug the term 2s over n. Here 2s over n, and here minus 2s over n. So as you see, here I will get s, but here I will get minus and minus, I get a plus. These two things will be with opposite signs. Because I had a minus, so the upper term will have a minus. But the lower term has a minus, and another minus gives me a plus. So I will get n minus, when I subtract this minus this, I get n minus n plus. So the next term will contain n minus n plus, n minus n plus, 2s over n. So this term comes from the second one. And now still I have to plug the last term, the term that is minus 2 squared over n squared of this plus this, which is again n plus 1. Remember, this plus this was n plus 1 with a minus sign. This has a minus, this has a minus, but since there is a minus in front, I will get plus 2 squared over n squared n plus 1. Is it correct? The plus I get there? Yes, that is correct. And I still have this last term, because all I did is I plugged here and here, but I have this last term. Now you can move it a little bit down, bar. I have the last term, which was the, and I am almost there, the minus 1/2 ln 2 pi n. Now I have this, but I have expanded till the power s squared. So I did an expansion until s squared of my expression. Okay, and now I am going to massage this into something that you can see quite easily. First of all, what is n minus minus n plus? This is minus 2s. Remember, n plus minus n minus was 2s. So I have minus 2s times 2s, I have minus 4s squared over n. And here I have 2s squared over n. Okay, this first term, well, I am doing the approximation. This is 10 to the 23, this is 1. So you will agree with me that I can write n. So this is 2 squared over n. And this is minus 4 squared over n. So that's a crucial step, that these two terms combine to give me something negative, which is minus 2 squared over n. That this term is negative, because this term is twice as big as this. So I have combined these two. This term, let me leave it again as n ln 2. I don't need the n plus 1. And I have, what else do I have left there? N lost 2 minus 2 squared over n. And I have the term coming from here, right? 1/2 ln over 2n. No, I didn't exact here. So I left n ln 2, and I have here a ln 2, because I have here a minus 1/2 ln 2. So when I combine those two, I get ln of square root of 2 over pi n. Is that correct? No. Yeah, plus. This is a plus, right? Yeah. Or if I want, I could have 1/2 ln of 2 over pi n. This comes from the pi n that I have here, but this 1/2 ln 2 combines with the plus ln 2 to give me plus 1/2 ln 2, and that's why it goes on the top. So this is the end of the story. This is the approximation to order 2, to order quadratic in S of the logarithm of g on n of ns. Okay, this is not g, this is the logarithm. Okay, so if I want g, I have to exponentiate that, and let me do that. So I will get e to the minus 2 squared over n. That's the key part, the decaying exponential in S. And all the rest is the part that does not contain the letter S. So if you want, I will call it the g of n0. But you can convince yourselves, or I might convince you, that the part that does not contain the letter S is the g if you take s equals to 0. What does it mean? Take s equals to 0, that we take the combinatorial n factorial, n over 2 factorial, n over 2 factorial, because that's what you get when s is 0. Remember, here you had n over 2 plus s, n over 2 minus s. So when s is 0, this number stands for this. And if you want, just, did I do it somewhere? Yeah. I do it, but well, it's an auxiliary calculation, but if you want to make sure I didn't cheat, just let me calculate that. Let me calculate how much that is. If I take the logarithm, it's the logarithm of n factorial minus the logarithm of n minus 2 factorial twice, okay? Or minus twice the logarithm of n over 2 factorial. Okay? That's this, if I take the logarithm of this quantity. It's the logarithm of this, minus the logarithm of this, minus the logarithm of this. That is n plus 1/2 ln n, and now I am not expanding in s because there is no s there, n plus 1/2 ln n minus n plus square root of 2 pi plus minus n plus logarithm of square root of 2 pi minus twice n over 2 plus 1/2 ln n over 2 minus n over 2 plus logarithm of square root of 2 pi. All I did is I wrote it for n, and here I wrote the same, but for n over 2, but with the factor 2 in front. And you see the factor 2 in front is what makes a bunch of terms cancel. This minus 2, n over 2 is the number n, which cancels this number n. As always, that part always cancels. And here I have n plus 1/2 ln n minus n plus 1 ln n over 2. So I have n plus 1/2 ln n minus n plus 1, because I am multiplying by a 2, ln n over 2 minus twice ln square root of 2 pi. Let me see if all that is correct. N plus 1/2 ln n minus n plus 1 ln n over 2 plus logarithm. No, I don't have 2 because here I had 1 times this, and here I have minus 2 times this, so I have minus 1 times that. Okay, sorry. Okay, so that's what I get so far. Now in the last step, I do the usual thing. I write this as n plus 1 minus 1/2. So n plus 1 ln n minus n plus 1 ln n over 2 is just n plus 1 ln 2. Because I have ln n minus ln n over 2, which is the ln of n over n over 2, which is the number 2, ln 2, sorry. Ln 2, I got rid of all the n's, and I have still, I put here n plus 1. So I have minus 1/2 ln n. This one I have left because I put n plus 1, I get minus 1/2 ln n minus ln square root of 2 pi. And so far, so good. No approximation. And what is that? I have n plus 1/2 ln n. N plus 1 ln 2, I got that term, minus ln square root of 2 pi, that's okay, minus 1/2 ln n, that's okay. And that, how do I combine it to get the result I need? N ln 2 is the ln of 2 to the n. I want to take lns all over because I am trying to calculate a certain quantity of which this will be the logarithm. Ln of 2 to the n square root, on the bottom I have square root of 2 pi Here I have square root of n, 2 pi n. Is that correct? I can combine this as 2 pi n. And I have still left the ln of 2. And the ln of 2, so I can put it the 2 on top. So I get square root of 2 over pi n. And now it's correct. Yeah. So that means that my g of n0, which is, this was the logarithm, is 2 to the n square root of 2 over pi n. And you can go and check that that's what I got before. Okay? Go move it a little bit up, so you will see that exactly that factor is what I had there left. Okay? What I had there, move it a little bit up, was exactly log of 2 to the n square root of 2 over pi n. So I got exactly the same. So now I have the final result that I can discuss and analyze. So let me open a different page or click there, please. And so I am writing here the final result now, which is square root of 2 over pi n e to the minus 2 square over n. This is my g of ns. This part, 2 to the n, sorry. I have a factor 2 to the n outside the square root. That's okay. And actually, you can convince yourself that this is the right result. How do I know that this is correct? Well, do the simple following thing. Integrate this from minus infinity to infinity, the g of ns. Now, this has to give me all the states in the system, right? This is the number of states associated with mismatch S. Remember, S is the number of spins up minus spin down, or that over 2, if you want. So if I sum over all S, I am summing over all states of the system. In reality, I need to sum from minus n over 2. Remember, S went from minus n over 2 to n over 2. But, you know, when n is 10 to the 23, and this is an exponential decay, I can write from minus infinity to infinity. And this is square root of 2 over pi n 2 to the n times the integral of e to the minus 2 square over n from minus infinity to infinity. You see why I taught you to calculate Gaussian integrals, because now we know how to calculate that integral immediately. And this integral, remember, is square root of pi over alpha, where alpha is what is in front of the s squared. So this is square root of pi over 2 over n, or square root of pi n over 2. So this integral gives you exactly square root of pi n over 2, so this whole sum gives you just 2 to the n. So that means that my Gaussian approximation, in which I write finally the g of ns as the value of the maximum times something that decays exponentially in s squared, is consistent, because I sum over all states and I didn't cheat, because I get exactly 2 to the n. So this is, in principle, this is called the Gaussian approximation to the binomial distribution. So this is valid. The only thing that I use is that n was a very big number and that s over n is small. Okay? So, but what is it that I get here? So now let me think. What is it, the physics behind all this? I calculated all the states. I saw that for the case when n was 5 or 6, we had a maximum when s was 0, which is what we get here. We get a maximum when s is 0, and in the case when s is different from 0. But let's say that n is, I don't know, some reasonable number, 50. Even if you get an n as big as 50, what do you have here? This number is the approximation to 50 factorial divided 25 factorial, 25 factorial, which is the g of 50, 0, s equals to 0, right? S equals to 0 is when you have 25 plus s over 2, 25 plus s, 25 minus s. When s is 0, is this. This number for 50 is approximately 1.27 times 10 to the 14. I'll show you in the computer a little bit the approximation. So that's the maximum, multiplied by 2 to the n. So all this. So there is a very big maximum. For 50 particles, if you have 50 spins, there are already 10 to the 14 ways of states which have 25 spins up and 25 spins down. But if you go away from that, you have 26 spins up and 24 down. That corresponds to s equals to 1. And if you have 27 spins up and 23 down, that corresponds to s equals to 2, and so on. So you see, you decay quite fast from the maximum. You have a maximum and you decay exponentially. And if you want to know how fast you decay, well, let me do it here. Oops. Another page. Yeah, go back to the other page. Okay. Okay. So let me look. Is it here? Yeah. So let me look how it decays. If you have something that is the g of n0 multiplied times e to the minus 2 squared over n, well, when does it decay to a value? It has a maximum and it's a decay Gaussian, right? E to the minus s squared. I will plot it in a second. But, you know, when does it decay to a value which is 30% of the maximum? When this number becomes minus 1, okay? When 2 squared over n becomes 1. Because then I have e to the minus 1, which is 0.3. So if 2 squared over n becomes of order 1, already the function is at less than 30% of the maximum. Okay? So that tells you this will happen when s squared is of order n over 2. Then 2 squared over n is of order 1. Or when s is of order square root of n over 2. Or s over n, the fraction of spins that points the wrong way is 1 over square root of 2n. So you see, remember, this is 10 to the 23, so the square root is 10 to the 12 still. So if 1 in 10 to the 12 spins points the wrong way, that means instead of having exactly 50-50, half of the 10 to the 23 pointing up and 10 to the 23 pointing down, that's a very big number. But if already 1 every billion spins points the wrong way, already the probability is much smaller. 1 in a billion spins. Imagine the probability of 1 in 100 spins to point the wrong way. We'll do it numerically in a second. But you see, that tells you that this function is extremely sharp. It has a maximum for the case 50-50 and it decays very fast. The probability of finding 51% of the spins up and 49 down is much, much smaller than the probability of 50-50. The probability of finding 50.000001 up and 49.99999 down is already a number incredibly much smaller than 50-50. So this is very sharply peaked around the maximum. That's the whole message here, that when you have such big numbers, the distributions have a maximum state, which in this case is obviously the case when there are 50-50, and anything away from it falls extremely, extremely fast. So I will try to make it a little more quantitative. So you see, if you calculate G of n0, we say this very big number. If you calculate G of n1, which is what we call having n plus half of the spins plus 1 pointing one way and half of the spins minus 1 pointing the other way, well, this number is not that much smaller than the other, right? Because imagine that, let's continue the case when we were saying that n was of the order 50. And we said that G of n0, which is the combinatorial 50-25, was around 1.26 times 10 to the 14. And I am doing n equals 50, not n equals a gazillion. Already it's a big number. If you calculate the probability, you divide G of n1 over G of n0 to see how much smaller is the probability of pointing one wrong. Well, if you go to the other expression, what do you get? The G of n0 cancels, and you get e to the minus 2 over n. Okay, because it was e to the minus 2 square over n. If s is 1, you get e to the minus 2 over n, and if n is 50, this is e to the minus 0.04, which is not a very big number. So this number will not be that much smaller than the other. So the chances of having between 50 spins, the maximum will be 25 on 25. 26 on 24 still gets a reasonable chance. But we are talking about 1 in n. But if you calculate instead of that the probability of having G of n, say n over 50, divided G of n0, which means having 1 every 50 spins pointing the wrong way, you get what? E to the minus 2 s squared, which is 50 squared, divided 50. Okay, it was e to the minus 2 s squared over n. Okay, so I have here, whoops, if I put that, I get n over, sorry, no, I'm putting the wrong numbers here. I am trying to calculate this, so this will be e to the minus 2 n over 50 square over 50. Okay? And this number will be, here I will have n squared, which is 2500. The denominator should be n, sorry. Oh, absolutely. I was calculating over G over n. So here I'll have n squared, but here I'll have an n. So I will have e to the minus n, because I have n squared over n, and here I have 12,050. Okay? So what is this number? If n is a very big number, if n is 10 to the 23, you understand that this is 0. So the probability of having one spin pointing the wrong way, okay, that can happen. 2 spins can happen. But 1% of the spins, the chances are so much smaller. We are talking about e to the minus 10 to the 23. That essentially is 0. You will never find the state if you are doing statistics, which is what we will have to start doing now. You don't need to count the states where 5% of the spins point the wrong way or what, because they are statistically very insignificant. And you will see that many of the thermodynamic properties that we will learn next time follow from that fact, from the fact that you have one state that has the maximum of probability And most of the states that deviate even a little bit from that have a very, very negligible probability. So let me now actually show this to you in the computer before I do some statistics. And I have here, I open the mathematical file where I approximated simply the Gaussian by open another one. What was it? Why did it
Top
close?
left.
Ah, here. Okay. I wasn't seeing. Okay, so this is what I showed you last time. So I don't want to show you again, but you will see underneath, this is the approximation to the factorial. Remember that we discussed last time. But here, what I did is I wrote the g of ns, which is exactly the expression I was using. Square root of 2 over pi n. I mean, I divided by 2 to the n. No, I have it even with the 2 to the n. So this is exactly the number of states for n particles with x spin s. This is the mathematical function. And I wrote it here for the case when n goes from I asked it to plot it from n going from, no, this is the g of n0 to see how much it goes. No, that's not interesting. What I have here, which is more interesting to you, is, oh, here I was comparing my g of n0 with the actual factorial, n factorial over n over 2 factorial squared, to make sure that the approximation is quite good. Okay, so the Gaussian approximation to the main factor, the maximum, you get it until, what did I get it, for the first 30 numbers, quite reasonably. But here underneath, I did the actual distribution. Okay, in the first case, I did it for when n is 10. So you see I got a g of 10s, 10 particles, and of course s goes from minus n over 2 to n over 2. I wrote it explicitly. And so numerically, here you have it. This is the Gaussian approximation to the binomial for 10 particles. And here I plotted it. That's what you get. The maximum is around 250, and it decays this way. So it's a soft decay. This corresponds to 0 spins up, 1 spin up, 2 spins up, 3, 4, 5. This would be the maximum. Okay, but more interesting than that, then I asked the computer to do it for bigger numbers. So here I have it for 50, and here you can see that the Gaussian expression, when I plot it, it very much looks, it's a Gaussian curve, but this would correspond to 25, to s equals to 0. And approximately here, I will have s equals to 2 or 3. Here is s equals to 10. Already in s equals to 10, the maximum is 50, I can neglect that. So, and then I did it even for a bigger number. So to see that this Gaussian approximation, here I did it for a 500, I believe. Okay, so this is 500. So the state with all the spins up will be up there. But you see, they are all 0. Essentially, if you move away, so the maximum is around 10 to the 300 now. It's a very big maximum, and already I have 3 orders of magnitude smaller, so the scale, I cannot even do justice to the scale. But if I want to see the states that have a probability 10% smaller than the maximum, are only here. So are the states with 5, 10 spins down. but already 20 spins down or 30 spins down, 30 more than 50-50, I mean, are very, very negligible. So you see, that's the message. So if you try to extrapolate in your head, when n is 10 to the 23, you will get a maximum that will be 10 to a number that the computer will not be able to plot, but it will fall so sharply that you will see practically a big peak here and nothing else, and the rest is zero.
Does this function tend towards the delta?
Yeah, obviously. So in the limit, this would be a delta. That you have one state with a lot of probability and all the others with zero. So in the limit, the Gaussian is an approximation for the delta. That's a very good point. For those of you who know a little bit of delta functions, one of the ways of expanding delta functions is by writing a very narrow Gaussian that the maximum goes to infinity and the thickness goes to zero. So in the limit, that's what you get. That you have one state whose probability is so much bigger than any other possible states that it dominates the whole distribution. Okay, what does all this mean for statistical physics? So, and the instance displays that now, do you want to the other one? Okay. So, what does it mean for statistical physics? So, we got a distribution. What do you do in statistical physics with distribution? Well, you calculate the averages of the quantities of interest in your system. Whatever you are interested in studying, you calculate. Okay, so can you click there?
That's not down.
What?
Not down. This way?
Yeah, click on a new page. So you see, each state has a certain probability, P of S. And remember, we calculated for S equals to 0 was a certain number, S equals to 1, S equals to 2, what I called before G of NS. But, you know, in general, for an arbitrary N. Okay, so each state has probability S. So if you want to calculate the value of any quantity in your system, and that quantity depends on S, as example, for example, we saw the energy, so we have any magnitude F that depends on S somehow. For example, remember the energy was minus 2S mB. So there you have, it's a function of S. But you can have any other quantity that depends on S. How do you calculate the average? Well, you sum F of S times P of S over all S. That's what you call the average of the function F of S. Right? So that's what you learn in statistics. You take the value of your function on each of the possible states, but you average with the probability of those states. So you see that immediately this will be where this P of S must have the property that the sum of P of S has to be 1. Because if it is a probability, they have to add up to 1. And so what will be our P of S in this particular case will be the G of NS divided 2 to the n. Why? Because the total number of states is 2 to the n. So when I sum all the PS, remember the sum of G of NS was 2 to the n. So when I sum the P of S, I get a 1. So this will be the probability, what I obtained before divided 2 to the n. Why? Because I have a bunch of states. I calculated the probability of each one of them. I divide by the total number of states, which was 2 to the n. So now I can calculate any quantity that I need to know. I can calculate, and this is a problem in statistics. Or those of you who took a course in probability, you must have done this till you got sick of that. So, for example, let me calculate the first quantity, the average value of the excess spin in my system. Okay? Because remember, S takes different values, sometimes it's 0, 1, 2, all the way to n minus 2, n over 2. So what is the average value of S? By definition is S g of ns over 2 to the n integrated from minus infinity to infinity. In theory, from minus n over 2 to n over 2. If you have a discrete sum, but in the limit it's that. I don't have to tell you what that integral is. I am sure you can calculate. Remember, g of ns is some constant times e to the minus 2 squared over n. A perfectly even function. So when I multiply by s, I get a perfectly odd function. This integral will be 0. Okay? So this will be 0. What does it tell me? That there are as many states with 5 more spins up than down, that there are states with 5 more spins down than up. When you average all of them, the average value of the excess spin has to be 0.
Yeah.
Because for each state that has a certain positive excess, there will be an equivalent state with the same probability that has a negative excess. You saw it when we wrote the numbers before. 1, 5, 10, 15, 20, 15, 10, 5, 1. Okay, for the state with 4 spins up and 2 down, you have this. And for 4 down and 2 up, you have this. For 1 and 5, it's totally symmetric. So the average excess spin, it's not too interesting to know that it's the number 0. More interesting is this, because this is a positive quantity. For any system, the square of the excess of spin is a positive number. It's 0 if the state is perfectly matched, and it will be a positive number otherwise. So this is what appears in the fluctuations. If you study probability, you know that the square root of that is the standard deviation, etc., etc. So let me calculate that. So this is, I have to do 1 over 2 to the n, and I have to do the integral of s squared g of ns ds. Okay? Remember, the probability was the g divided 2 to the n. Because remember, the g goes to 10 to the 50 or whatever, these crazy numbers. But when you divide by 2 to the n, it's a number between 0 and 1. So what is that? That is 1 over 2 to the n. Let me write the g. Remember, it contains the factor 2 to the n, square root of 2 over pi n. All that goes outside the square root, and I get s squared e to the minus 2 s squared over n ds. Yeah, okay. So these are constants. So by the way, this is cancel precisely. And this is the integral you have to do. And again, these are the useful Gaussian integrals. This is the I2. Remember, I2 was something to the square times e to the minus that something squared alpha. This plays the role of alpha. So we know what that is. This is the I2, where the alpha happens to be the number 2 over n. So that is square root of 2 over pi n, which comes from here. And the I2, look at your notes, was square root of pi over twice the alpha to the power 3/2. Right?
Yeah.
The alpha, and the alpha is 2 over n. So I have here 2 to the n to the power 3/2. That's the result. Let's see what all that means. Well, first the pi's go away. I get n to the 3/2 over n to the 1/2. I get a factor n. And then all I get is square root of 2. Here I get 2 to the 3/2, but here I get 2 to the 1/2. Is 2 to the 1 and another 2, I get a 4. So this is n over 4. Is that correct? Yes. S squared is n over 4. What does it mean? That the excess spin, which was 2s, if you square this and you take the average, you get the number n, because you get a factor 4 here. So the average excess spin is of order n. And this at times is called the square excess spin, and this has a lot of meaning. This means, for example, that the standard deviation, which is the square root of that number, goes as square root of n. The standard deviation of the excess spin is n. And if you divide the standard deviation as usual to get the fractional fluctuation, the square root of 2s squared over n, you get 1 over square root of n. Those of you who took probability will recognize this result, that the standard fluctuation is incredibly small. This is 10 to the 23, so the square root is 10 to the 12. Next time when we start discussing thermodynamics, we will have to do a few numerical estimates. But here you get it, that the probability of having a certain fraction of spins pointing in excess of the perfect alignment goes as an incredibly small number, okay? So if we have 10 to the 20, this is 10 to the 10. So it's likely that if you have any fluctuation in your system, any number of spins that point the wrong way, that fluctuation would be a fraction of 1 spin in a billion or 1 spin in 10 billion at the most, because this is 10 to the minus 10. Okay, so probably the most likely thing, not always will you pick states in which you have exactly 50% and 50%. But if you do this experiment a gazillion times and you count each time how many, and you pick states at random, and you count each time how many spins point the wrong way, if you average that, you will get 0, because we said you will find as many states in which you have an excess of positive spins as you have an excess of negative. But if you take the square of that quantity and you calculate the standard deviation, will be of the order of 1 spin in 10 billion. So in the typical case, you will not get more than, if you are not going to get 50-50, but you are not going to get more than 1 spin in 10 billion pointing away from 50-50. Which means that the system is totally dominated by those, okay? So that's the idea.
So we derive this from the mathematics, but regarding of physics, when you look at the macro states of things, is that related to anything about the second law of thermodynamics?
Oh yeah, absolutely. Next time we are going to do that. We are going to consider what leads to the second law of thermodynamics, which is what happens when you take more than one system. You take two systems, each is given by this distribution, and you put them together. And somehow energy can be exchanged between them, which is what happens in thermodynamics. So that means that the total system is isolated, so the total energy cannot change. But, 3 spins can flip the wrong way here, and 3 spins flip the other way there, because then the total energy is the same. Because remember, total energy depends on the total number of spins up. So if 5 spins here go that way and 5 go that way, that's a fluctuation. And we will calculate in which direction this will happen, and you will see that it happens in the way that we call the second law of thermodynamics, goes to the states of highest energy. We will calculate what is the most likely state when you mix two systems. They don't have to be in their maximum state. So imagine that you get a bunch of spins and you put them in one way and another in another, and you put them together. What will happen when they can exchange? And so spins can flip. There is some residual interaction, and we'll calculate, and you will see precisely what I described here, that there is one definite direction in which things will happen, and that's the content of the second law of thermodynamics. By the way, this would be an excellent time during this week, while I am finishing, which I will finish next time with a few general ideas of probability, to review those of you, and now I'm speaking only to those of you who didn't have any notion of thermodynamics, to take the book that you used in Physics 1, Physics 2, and read a little bit through the chapters. Because what we will do starting next time is starting to get the statistical definition of temperature and on entropy and so on. But it will be very useful if you keep in the back of your mind what people call temperature in thermodynamics, what you measure with the thermometer, that heat can be exchanged, that if one body loses heat, the other gains, which is called the first law of thermodynamics, and that systems tends to equalize the temperature. So if those ideas, you can compare the results that we discuss here statistically with the intuitive ideas of thermodynamics. As I said, we will come back to those, and using the book of Fermi, we will derive them more carefully. But it will guide you through the discussion. This is sort of chapter 1 of the book by Kittel. And next time I'm going to start in chapter 2, which introduces the idea of temperature and entropy in the context of this model, in the context of binary systems. Actually, before I do that, I want to do one more exercise of cementing these ideas by giving you another model, which is a typical example of a binary process, which is very famous in the history of statistical physics. In reality, statistical physics started with it, which is the random walk. The process in which at random you take a step in one dimension, in which at random, you are here, and with probability 50% you take a step to the right, and probability 50% you take to the left, and the next as well, and you look where you end up with. You will see that this model is exactly the same as the model we have been discussing, okay? If we consider that the probabilities are 50-50, because then, if you look at the final position, where is the final position? Is the number of steps to the right minus number of steps to the left, right? If you, let's say, a random walk of n equals to 8. If you give 5 steps to the right and 3 to the left, n plus minus n minus is 2, and that's where you end. So our old excess spin is nothing else than the final position of a random walker. What I will do, because I don't want to do the same mathematics again, because this one will be exactly the same, I will do a little twist on this model, the model of what we call a biased random walker. A walker that walks here, in which the probability of moving to the right and moving to the left are not 50-50, are say 70 and 30 or whatever. So there is a probability P at each step to give a step to the right, and a probability Q giving a step to the left, P plus Q being 1. So for P equals 1/2 is exactly what we have been discussing, and you will see that the results we will obtain when you replace P and Q by 1/2 are all the old results. But it's interesting to understand what will happen in this case. What is the final position? What will be the fluctuation in the final position, etc. in this model? It's still a binary process, you understand, because at each step there is only 2 possibilities, right or left. Although the probabilities are not the same, still there are 2 possibilities, so it's binary. And each step, that's why it's called the random model, is independent of the previous step, which is the same as saying that this spin points this way and the next spin is totally independent of how this spin points, okay? It can be up or down. So you see that there is a total analogy. This corresponds as going 2 steps to the right and 1 to the left and so on. There is a total analogy between random walks and binary steps. Actually, the people who developed the idea of probability, Laplace, etc., were thinking in terms of random walk. So I'll repeat a little bit of the random walk, but for the case of the biased random walk, and that will allow you to do a few exercises on your own. I will give you just go to the computer and do a random walk and check that all the analytic formulas we obtained here are verified. And what else will I do? I will show you that if you take expression of the random walk and you just expand it like any quadratic expansion, you get precisely the Gaussian approximation that we obtained here. It's nothing else than doing a quadratic expansion around the result. So that we will do next time. That will take us perhaps half an hour or so on. And then we can move to try to motivate using this binary distribution the main laws of thermodynamics. So that's where we are heading, which is the content of chapter 2, if I believe in the book by Kitab. So we'll do probably chapter 2 and a little bit of chapter 3, and then I'll let it go and we'll go to kinetic theory. That's where we start. Okay, let's stop here. I will give you a few problems in probability for you to play a little bit. Some of them require the Poisson approximation to the binary, which I didn't discuss yet. We will discuss it next time. So the Poissonian, you can leave for the time being, but the others you can start playing. And you know, these are the typical problems. What are the chances of getting a poker if you pick 4 cards from